So, good morning, everyone, and welcome to the Open Source Firmware Conference 2019. I'm Philip. I'm the founder of the conference, so probably you have seen me before. First of all, I want to thank our sponsors and especially the co-organizer, David Hendricks from Facebook and Chris Koch from Google, for helping us to realize the conference here in the Silicon Valley, because without them, it haven't worked out, so that's really good. Thank you. Big applause for them. So this year is a special year because we have the 20th anniversary of Coreboot and U-Boot open source firmware. And so let me introduce you to Ron Minnick, giving the keynote, and enjoy the conference, have fun, and probably can chat and meet. So have a nice day.
No, I'm wired. Yeah. If anyone here is from organized crime, don't kill me, but I am wired. So this is a talk I wanted to give about the 20th anniversary, because 20 years goes faster than you'd imagine. And there's some interesting perspective about this project. And I think part of it is was not a project destined for success. In fact, this project basically almost died 10 years ago. So that part is interesting. I've been accumulating bits and pieces of slides and stuff starting about 6 months ago, found some stuff that I'd forgotten about. David just reminded me some other stuff I'd forgotten about, like the, almost fake intern death we did at Los Alamos, but I didn't find that picture, so we can talk about that one later. I've left a lot of stuff out. This is a personal view. This is not representative of Los Alamos, Sandia, or Google. This is just me talking about my memories and what I found and that kind of thing. So in 1999, I'd been working on supercomputing for over 10 years. I've been doing clusters on workstations and PCs for about 8 years. And I moved to Los Alamos. So weirdly enough, I realized that you really can't see it, but the person with no gray hair is me. And that kind of tells you what this kind of work does to you after 20 years. And the deal is you would open up a box and then you would wire up your own network. It was all do-it-yourself back then in supercomputing for clusters. And the thing that I began to realize after a while is how much I hated the BIOS, like with a passion. Why was that? Well, it took forever to boot. It took 5 minutes to boot. It actually takes longer now, but back then 5 minutes was really horrendous. And to update the firmware on all 128 machines, there's no bugs in firmware. But anyway, when there was a bug, you had to carry a floppy around and you had to have a cart with a video device and a keyboard. And that hasn't changed much, except now it includes a mouse. So that's kind of odd. And then if things went wrong, what if things went wrong? How did you fix it? You just had to yank the node out and move the jumper to a recovery BIOS, which had no keyboard and mouse. So you put the floppy in, and you're in a machine room with all these fans, and you had to listen for the beeps, because it ran an autoexec.bat, and you waited for the beeps, and with luck, you could then recover. So this is really just incredibly awful. And that's kind of not changed. It's still incredibly awful. And the amazing thing too is, what was the deal? You net booted with TFTP, and we all knew that TFTP would be dead by 2010. Except, right, wrong. So the thing I realized is, wait a minute. There's copious documentation at developer.intel.com. Some things change. And we've got this great new free open source BIOS, and we've got a big RAM flash part. It's a 1/4 meg. Right, which is huge, right? It'll easily fit a kernel in a 1/4 meg, no problem. And so I thought, wait a minute, we can just put Linux in there, done. So we put Linux in Flash, and we started with something Stefan Reinauer did called OpenBIOS. And one of the things I realized is, well, if we're going to put Linux in Flash, we're going to have to have Linux able to boot a Linux kernel. And when we went to supercomputing one year with that idea, this well-known Linux person said, no way will that ever make it into the kernel. Even if you do it, it's a horrible idea. It'll never make it into kernel. It's true. Our version didn't make it, and Eric Hendricks' version didn't make it, but Eric Biederman's version did make it. So, you never know what's going to make it into kernel. There have actually been a fair number of these kernel boots, kernel implementations. Back in 2004, I did a paper about them if you want to look it up. And as usual, the cleanest one was the one in Plan 9. So some things never change. And here's my assumption. I kept thinking that this is so terrible that if we do this, we're going to hand it off in a year to companies like AMD and HP and Dell, because they're going to realize this is really cool. booting in seconds is cool. We've just removed their entire software burden because now all their Linux guys are their firmware guys. And yeah, we were kind of naive, but if you look at every single one of the top 500 supercomputers on the top 500 list, they all run software written at Argonne National Labs called MPI. Clean room was invented at Sandia. The Monte Carlo method, used very widely in supercomputing, was invented at Los Alamos. So you really can look back at a 60-year history of the DOE labs contributing to the computing community in ways that most people don't even know anymore. So it wasn't crazy to think that we'd do this new improved BIOS and we would hand it out and people would pick it up. What we didn't know is that the BIOS by year 1999 was a profit center. BIOS gave you vendor lock-in. BIOS gave you quote-unquote features to give to people. You know, BIOS did lots of things that we didn't realize it was doing in terms of the business model of selling servers. And that's in the end what really made that not work after a year. We're still there in the x86 world, and we're trying to work our way out. I think we're going to maybe in the next year, but we'll see. But there's an upside that I began to realize after not too long. The Coreboot source is kind of this library of knowledge about how stuff works. And a lot of that knowledge was lost before we started this project, and a lot of it has come back and actually been lost again, but that's another story. You know, and the day it really hit me full force was DRAM setup. Anybody who's ever done the mode register set, you got to shift the bits left 3 bits. Why do you have to shift the bits left 3 bits? It took me 2 months to remember this because it was something I'd known 20 years earlier, believe it or not, doing firmware on a Z80, okay? Because 3 bits or 2 bits or whatever, the byte line select. If I want to write an address hex to DRAM, I got to shift it left to make sure that's the address that goes to DRAM. I'd known this, okay? I'd forgotten it. And so what I saw happening, people figuring things out and realizing them in code, and then that code is sort of a permanent record almost, except for the times we drop a platform of how things work. I'll talk about the fast user interface in a bit, how we learned where the best place to put graphics startup is. It's in source, but it's in Coreboot, not in a kernel. That was a surprise. SMP startup, we did the first real SMP startup that was pre-Linux and really implemented it. We didn't really know how to do that until James Hendricks did that. And then there was this funny thing I did, reverse engineering K7 memory MSRs. I went back far enough in the Git tree, it's there at that hash, and you know, it's kind of funny. We had to do that. We enumerated the space of 4 billion MSRs overnight, run one night to find the hidden ones in the K7, and that's how we got DRAM working on the K7. So there's just stuff in there. We actually had a Romulator. We had a thing called the web config. This is actual screenshot. Thank God for the Wayback Machine, because I couldn't find any of this stuff. Our web pages are long gone, of course. Second lesson, put your web pages in Git or you'll be sad. But you could do stuff like this, right? You could say, hey, you know, I've got a lead tech. So, you know, give me a config file. It gave you a config file for that thing. Then you built Linux BIOS, as it was called at the time. And then, you know, away you went. Well, the problem there we didn't realize is the vendors were throwing little minor wiring changes into these motherboards all the time. So if I got a lead tech WinFast in March and I got another one in July, they were wired differently. Some GPIO was moved and the difference was buried in the BIOS. So this was kind of a nice idea that didn't work out in the end because of the variability in the hardware. That was something we didn't suspect. So we were in assembly for a while. And again, you can actually find the original commit. And this is an extract from the Wayback thing. Jeff Garzik came by and made a big contribution. He said, hey, there's a guy named, just forgot his name. Sorry, Jan Rydberg is right in front of me. He's written this kind of thing in C that I think you could build on and would be a better foundation because you'd have less assembly code. So this is the announcement on the web page of the commit where we actually made the cut to having about a dozen assembly code instructions and the rest in C. So that was a big jump. And all through this time, it was sort of iterate, burn, see how far you get, watch DRAM not work, watch DRAM work, watch IO not work, watch IO work. And, you know, we hit this wall, and I talked about this last year where we got stuck on PCI. And it turned out the problem was Linux, and we most recently discovered this about a year and a half ago, can't always configure an unconfigured PCI bus. And this still happens. If you boot Linux and you haven't run all the UEFI Dixies, Linux occasionally will stumble over, in this case, AHCI, and not be able to turn AHCI on. So we have patches for that. It's an ongoing problem. I think it'd be a neat policy for anyone in the Linux community to just commit to always booting Linux on something or other, just to see if it can really boot when nothing else is turned hardware on. But you know, many kernels assumed in 2000 that BIOS did the right thing, and if you didn't do what the kernel expected, well, you get something like this. See the thing in red. If one of the 4 base address registers was 0, that meant that, quote unquote, it was disabled, which in this case, of course, means not enabled. So the old confusion between disabled and not enabled crops up over and over and over again. Common thing. Okay, now, in May of 2000, the Park Service set a controlled burn in Bandelier National Park that became an uncontrolled burn and decided to go east, not west, and tried to burn down the entire town of Los Alamos, including the area where the plutonium was stored. And it did get stopped, which is good. They only lost about 450 houses or so. But meanwhile, here I am. If you look, I kind of said, hey, first login on the 440GX, then there's a month. It didn't take a month. It took a couple of days. It's just that that background there is kind of what was happening in my town at the time. It was trying to burn down. So that was kind of funny when I looked at the old, you know, the history and thought, oh, okay, that's why it was a month. But anyway, it would have been faster. Graphics was a continuing issue then and now. So and this is kind of, oh yeah, well, how much time do I have left? Half an hour. Oh God. I'll move faster. So we had to go with blobs in 2001. There was no choice. David did a lot of that work. I worked on it too. We had to get the 32 to 16-bit trampoline from 2-kernel Monty, implement a PCI BIOS. We grabbed the x86 simulator from X11. All that code has changed, right? It's still the same thing though. We're stuck with blobs for graphics even today. So the blob argument won't go away. It just came back again in the last few days. But you know, I don't like blobs. I don't want to have blobs, but don't get down on people too much because there are some blobs in the image. It's just going to happen. ROMCC. We could not get hypertransport working on the Opteron, period. It was just too darn complex. You know, and you needed hypertransport up before you could really kind of configure memory. So that meant you were trying to do it in assembly code. And it was just really an impossible situation. We couldn't figure out how to make caches RAM work. So the story as it was told to me from Linux Networks where Eric Biederman worked is he literally vanished for a month. Nobody knew where he was. Nobody knew what was happening. And he reappeared with 13,000 lines of actually pretty darn good C code that implemented ROMCC. So, you know, this is kind of, to my mind, sort of genius at work there, right? Somebody goes away, comes back, and he's got a C compiler that always inlines and uses only the register set as its memory. ROMCC made hypertransport possible. So, you know, take a look at that sometime. It's actually a very interesting piece of code. Is there any, Martin, is there a single board still using it? I forget. Yeah, so 15 years of this C compiler, and you know, sort of, there aren't a lot of people who found a lot of bugs in ROMCC. I just think it's an amazing piece of work. So, and then victory. So 4 years in, Lionel committed $6 million to build a 1,000-node Linux cluster, which we called Pink. We called it Pink because that was like the maximal way to annoy our management, because all the other colors were like white and blue and red. Guess why we called it Pink. So, but it was a 10-team machine, which at the time was really big. It would have put us on the top 10 of the top 500. And, you know, so I was looking at that and I noticed this thing at the bottom, booting Windows 2000 from a full open source code base. So the first Windows boot was in 2002. I'd forgotten about that. Gotta love the Wayback Machine. But, you know, to get a supercomputer commitment like that was pretty amazing. Pink was a 10TF machine. The DEC Alpha machine that was also a 10TF machine was a $60 million machine. So that was kind of an interesting comparison. So this is what it looked like back then to build a supercomputer. You know, guys would show up and they'd sit there and wire stuff for like a week. And then they'd spend time finding a bad fiber. There weren't many. Little mention here. On the right is Eric Hendricks. He did 2-kernel Monty. He did bproc. He did a lot of incredible stuff. And on the left is Greg Watson, who did the PowerPC port of Linux BIOS. So this kind of went at lateral from, this will never work, this is a terrible idea, let's go spend some money on it. And that kind of is a good, that happens a lot more than you realize. And generally, if people say it can't work and it can work, that's a good sign that you should just go ahead and do it for what it's worth. But then we thought, well, it's all about HPC. That's all we did, right? Linux BIOS was always conceived as the base of a stack of software. Then Tyson Sawyer wrote to us from iRobot and said, yeah, we use it in a PackBot because mind-finding robots that boot in seconds are better than mind-finding robots that boot in minutes. Can't argue the point, right? And then Hamish Guthrie said, there's a TV that's made in Turkey, the digital TV, and TVs that boot in a second. Again, you know the rest of that punchline. It was also used in the military modem. And then Rob Armstrong and Mitch Williams had this neat idea, which was to take a pile of parts that look like that and assemble it into that. That thing was a lot of fun. You could kind of drop kick that and it would work because there was only one disk and he mounted the disk well, but it took incredible amounts of abuse from airline baggage handlers. And every time we plugged it in and turned it on and worked, and we had it until they reorganized the building at Sandia and they put it in a box and it went into the Indiana Jones warehouse. We think it's still at Sandia, but nobody knows where at Sandia it is. So, oh well. But that inspired a lot of other good ideas. So that one on the right we called DQ. It was a CD case holding a bunch of things. And then, that's a build session at the top left at my house. So the mini clusters were really cool and continue to be cool. And then from there, we got the R&D 100 award. And the funny part is that's a mini cluster there. The award was for the 1,000 node machine, but a lot of people would look at the mini cluster and say, how the heck did you get 1,000 servers in that little box? So, I guess it's the importance of labeling. But the neat thing was it was 1,000 nodes, one disk. They shipped it from Salt Lake City to Los Alamos. The disk failed. The only thing that broke in the whole thing in shipment was the disk. And they said, no problem, we've got a backup disk. They took out the backup disk and it had failed too. So this is why I really, really hate disks. But, this is part of a stack. Linux BIOS was a part of the stack, but it wasn't really the thing that made Clustermatic Clustermatic. You saw Eric Hendricks there. He was kind of the key guy on everything above Linux BIOS. We even ran a class. This is kind of fun. This is a class at UT Austin. And the deal was, I didn't know IBM did this. I doubt they do anymore. You'd call IBM and say, can I have 24 ThinkPads for a loan for a couple days at a conference? And they'd come in those big blue boxes. And, it was pretty awesome. And then we ran this class, and you can kind of see here, these are two little systems. And in a class, people would build Linux BIOS, burn it on that, and then boot our cluster stack. So they would actually build like the 1,000 node cluster. They'd build a 2-node version of that in a day. And it was just kind of educating people on how this software stack worked. So cache is RAM. I was at UNM one day and somebody said, talk to this grad student. He's from Intel. He can tell you how to do cache as RAM. You're not doing it right, which we already knew that because we couldn't get it to work at all. And he said, oh, cache as RAM is so easy. You just aren't reading the manual carefully enough. And he said, look at the cache disable bit. And I said, yeah, it turns off the cache. He said, that's not what it does. The cache disable bit does not disable the cache. The cache disable bit disables kind of going out to memory. And I said, if you tell me this, you're going to get fired. He said, no, it's okay. I'm just reading the volume carefully. So we got cache as RAM. But that's like the original cache as RAM. There's 2 papers I found, which were kind of fun. And again, it's more knowledge realized in code. And this is where I don't think FSP should take this over because then we lose that knowledge. And I don't like to lose knowledge. So that's kind of my one disagreement there on FSP. And this is the first Linux BIOS Summit. We had about 100 people. I have no pictures. Didn't go that far. The reason I mentioned 100 people because, well, let me digress to one laptop per child and see if anyone recognizes that person in that picture. So this is my room at home, and we were trying hard to figure out how the hell to make that Geo chipset work, and I can tell you stories. There's a reason Ollie Lowe quit the Linux BIOS project, and that chipset is it. But thanks to Steve Goodrich, who flew down, and Mark Jones and Jordan Krause, we were able to get it working. I also want to mention they eventually moved to open firmware. They moved to open firmware because open firmware had a command prompt that was active before DRAM training, and nobody could get DRAM training right. So it's just something to keep in mind. We don't do command prompts. That's been kind of our mantra, but every once in a while, maybe you should. So Now, notice I said 100 people in Santa Fe and Hamburg in '06. The bloom was off the rose here, so there's like a dozen people there. And Jim Inge, you're in that picture somewhere. You might see yourself. Jim Inge came and gave a talk about Agiza. And then this is when we started the hack sessions. We were in his hotel lobby till like 2 a.m. We would close the bar and drink beer and pull out soldering irons. And then one night, one of the hotel employees came out and yelled at us for not renting a meeting room, almost threw us out. But that's a pretty elegant place to have a hack session, right? You can see the painting in the back. So it was pretty cool. And this is where the C neat tech activity began. So this is also where taking pictures of crashed firmware began. That's a phone we found on the street in Hamburg. But this is Miniature Wonderland, and there's something we saw in Bochum. Top left is Peter Stuga's car stereo. That is the only video I have on YouTube that people still ask to see. We made a video of his car stereo playing a song. And people just love that car stereo because it's sitting in a cardboard box. And this is the last Linux BIOS snapshot I have. So at some point in '08, name changed because, true story, both Microsoft and Sun came to me and said, we want to use it, you got to get Linux out of the name. We can't look at it with Linux in the name. Take Linux out and we'll take a good hard look at using it. And they did, and they didn't use it. So what can I say? You know, we had our dreams, but it didn't quite work out. But, you know, the thing is, at this point, it wasn't Linux because you remember that big flash part? It was way too small. And it wasn't a BIOS deliberately, right? We didn't want to implement a BIOS. So out it went. Denver '08, remember I said there was only like a dozen people in '06? This is half the people who came to the '08 meeting. We really, you know, we were clearly on a downward slope. I'll get to that in a minute. We did get a little talk from Ward about the FSFU, and some of you might recognize Stefan in there. And a guy on the left picture is Jordan Krause, who really was incredibly helpful and supportive until he went on to other things. 2009 is Cake and Fig. So Patrick and Stefan and I met in Hamburg along with this 5,000 person Harley Davidson convention. So you're kind of sitting in a coffee shop and these things are roaring by in circles because you can't take a Harley too far before it breaks, I think. So it's just kind of rolling around. And then we're in a coffee shop one day and we realized they pointed all the speakers at us to chase us away because they didn't like our soldering iron or something. So we actually would like move a coffee shop twice a day so we wouldn't get chased out. The Cake and Fig was this huge improvement in our life, but weird thing, one ODM complained to us recently that it's too hard to use. So I don't know, what can I say? I think it's fine, but we do get that. So kind of the end of the beginning was '03, because the end of '03, Intel let us know that developer.intel.com wasn't going to really have any information on how to configure QuickPath, which meant we were done in server. And then things kind of went down, and then 2010 was kind of our near-death experience, and we came back. So 2009, this is a retirement party we had for Ed, our cluster that was alphas. And, it kind of went out and nobody was really pushing on PowerPC, so that kind of went out. So we ended up being an optional x86 BIOS. And, that was unfortunate because some Endianisms and x86isms did begin to creep in. You can see them. But more to the point, we were tied to a chipset world that was closing, right? So we locked ourselves in a room and the doors were all closing on us. And, AMD was with us for a little longer, but, at this point, Intel is basically out of there. And so this was an interesting chart. I took all the Git commits and just did a histogram by year. And, this is kind of, in my opinion, again, this is my personal view, that's where DOE started to fall out. I mentioned that $6 million machine. There was a clone of that was more expensive installed here in California. People in DOE wanted Linux BIOS. They kept getting told they couldn't have it. And then, in 2010, a bunch of us took a break. I think, now, Stefan may correct me, but my memory is when he went to Google, his thought was he was done with Coreboot for a long time. So, but then you see in 2011, Chromebooks kind of come back in. So in my opinion, this chart makes sense with those notes I added. HPC and Google were done. Linux networks went under. All the IoT-like things that had been in the 90s x86 things were now ARM things. We didn't do ARM. So the usage was not there anymore. Guys like Peter Stuga kept the lights on, but you really can see in that chart pretty dramatic evidence that interest had dropped a lot. So again, this is my memory, Stefan telling you this story. He's walking down a hallway and somebody says to him, "Hey, you're the Coreboot guy, aren't you?" And he says, "Yeah." And he says, can you get this working on a Chromebook in like 6 months? And, you know, he pulled it off. And so in 2012, all the x86 Chromebooks that came out from then and after were Coreboot. And then in 2013, when multi-architecture came back with the ARM, you know, and from that point on, things just kind of took off. And we did some other developments. So I did this thing called the fast user interface. Here's the deal. On a Chromebook in developer mode, it runs the VGA BIOS to get graphics up. In normal mode, Linux brings graphics up. And it bothered me that there was 2 different paths for bringing graphics up. So I mucked about with Coccinelli for a while. And then Simon helped me out with the kernel side. And then Furkan made the whole thing, you know, legible code. And then finally we had a, you know, startup in Coreboot. And the surprise was, my thinking was the fastest graphics startup will be Linux. Second fastest Coreboot, slowest to be the VGA BIOS. I was completely wrong. The surprise was the fastest startup was always in Coreboot. So we did this little movie, and I'm going to let you take a guess which one is the Coreboot-based graphics in source. Oh, no. Well, you get the point. So the one on the right is the Coreboot one. And it's interesting. That didn't work well at all. I guess it was loading. And actually, on some Chromebooks, the Coreboot-based graphics code, open source, was 5 seconds faster than doing the graphics startup in a kernel. So that was a result I did not expect. And then it got to be 2014, and Peter Stuga wired me up this thing. That's a 16 meg flash part. It went into a KGPE D16. And here's the funny part. I had Linux, and I had this thing called uroot, which is user mode, userland, and Go. I'd been running in QEMU for a year or so at that point. We dropped that unchanged thing into, it's a connector. We dropped that thing unchanged into, sorry, trying to fix the graphics. Anyway, we dropped that thing completely unchanged into the hardware, and it worked first time. I wanted to see how it would fail. But it was kind of a view of the power of, you know, using Linux as your firmware, that it just worked. And it was the same image later I used in a minnow and in a server, right? Literally the same image, and it just worked. So when you use Linux as firmware, a lot of effort just disappears from your life, because there is no such thing as a board port, just about. And, you know, so at Prague Embedded Linux Conference, I was there with a company called Horizon. And we had a Facebook node there running Linux boot, and a sign that said "Kick Me." And you know, we used to use the "Kick Me" sign at supercomputing, because the idea is just come up and hit reset on the node and watch it boot real fast. And that's when I realized that the "Kick Me" sign did not translate to many other cultures. Nobody knew what the hell we were talking about, right? It's like somebody said, "Kick me? What do you want me to kick? I don't understand." So I had to stand there and say, "Push reset and watch it boot real fast." Number here. That thing running UEFI over 8 minutes. That thing running Linux boot 20 seconds. So, you know, in fact, that thing net booted over 100 megabit Ethernet from an RPi so fast that we thought we had a bug for a while, and we didn't realize that it was booting so fast we hadn't seen the net boot happen. So, you know, I never get tired of fast boot because I don't see it that often, but that was a really nice example of why it's good. And then finally, this is from the Facebook page. This is the part I really like. Those 3 words, Coreboot, uroot, and Linux boot, right? So Arista, right, kind of big switch company. And it's not well known, but Arista actually ran Linux BIOS from the start, and then had moved to Coreboot, of course. They moved to this totally open source thing working with Facebook. So thank you, Facebook. But there's also a new direction this year. There's a project that we started called Coreboot. Coreboot's written in Rust. Coreboot is Coreboot without C. You know, C's been a good friend of ours for 50 years. It's time to give it a little retirement. But we like the Coreboot directory layout, tools, and assembly. There's a lot of good stuff in Coreboot to like. So basically what we do is we forked Coreboot, removed anything that looked like a .h or a .c, and took it from there. Talked to Ryan O'Leary or Ganshan or Prachi here. They're working on it. And we were really delighted with Rust. And Now, I was supposed to say 2 days, but I've got a typo. In 2 days, Ryan and I got the ARM v7 on QEMU working. You'll see his talk here in the next day or two. And then, a few weeks and the Hi5U is up and working, and we're loading a kernel, I think. So here's the part I really wanted to get to. What did we learn? Because it's a 20-year project, and I have personal views about what we learned. And I think what's interesting is we almost died, right? So we had this great early success. You can go to Linux Journal in 2004. I was amazed. There are probably 5 server vendors in there that said they work with Linux BIOS. They were all lying, but they said they work with Linux BIOS, so at least they cared. But, so we had that success, and after that, it kind of really went down for a while, and we had really great people in terms of the true believers, but you got to have companies, and we didn't have the companies. So we almost died, and then Chrome OS, at least in my view, brought us back. So I think sustainable projects encourage leadership transition. I was the BDFL for about 4 years, and I was ready to be done. Luckily, Stefan stepped up in 06. We had a lot of interesting days there. You got to tolerate different ways, different cultures express themselves, but if you have toxic people, get rid of them as soon as you can, or at least moderate them. You've got to be very, very careful. I've seen one community completely destroyed by 3 or 4 bad actors. I think the RISC-V mailing lists are having a little trouble now because they just don't want to do what they got to do. Email is a horrible, horrible, horrible medium. The reason there are best-selling authors is because none of us know how to write. I'll speak for me anyway. So you really want to get in touch with people in person when you're having a problem, because email sucks. So revision control, not a lot of people know it. We started out on CVS. Probably no one here remembers what that is. On SourceForge, we took this weird detour through ARC, which is now called Bazaar, which is the right name. Then we moved to SVN for a couple of years. That did well, but it was really clear at some point that Git was the way to go, and that happened around 2010. I think Patrick's the one who did that, but the cool thing that Stefan did, I still don't know how he did it, is he kind of got the revision history all the way back almost to the beginning. So you can check out version 1 and look around. I had a lot of fun doing that, when I was trying to get this talk together. You can still find people in Google who will tell you how horrible Git is and why our internal repo system is far better. Don't think that because we're using Git, this question has been resolved. It hasn't. Build systems, all the bad stuff was my fault. We started out with this BSD-like build system because I like the BSD build system. Then we had this Python tool, and it just got awful. And Patrick, and a lot of it is Patrick, but really helped. No build system is forever. We have build systems and all the arguments all the time where I work. The one thing I warn you against, the thing I see all the time is, this build system is really complicated. Let's go to a more complicated one to make it easier to understand. Never seen that work. Okay, so I'm a big fan at the moment of Cargo, which is the Rust thing, but it is pretty complicated, so I don't really know the answer. Code, perfection is the enemy of the good. Every project struggles with this. You were just struggling with it today. When do you take code that really isn't written the way you'd like to see it written, but you don't have time to fix it? And you kind of need that code. This is really a really hard problem. I'm beginning to think we need to, if someone really slams a piece of code, maybe you should ask them to take responsibility for helping, improve it. I'm not quite sure what the answer is. I just know that it's a problem in every project. You need to encourage experiment. You need to encourage things you think are stupid. But on the other hand, nobody gets to break the tree. So just something to think about. We also learned we don't always learn. So we had the Coreboot ports to the RISC-V in 14, 15, 16, 17, 18, and 19. Where's Philip Hug? Yeah. And somehow in 2019, we got the BIOS again. So there's this model called SBI, Supervisor Binary Interface. And the idea is you're running in kernel mode and you put a number in a register and then you do something, you trap to a different protection mode and you do a full save of all the context. And then you do something, and then you put an answer in a register, and you return, right? Classic BIOS model. Nothing new there. It's 1979 all over again. Well, guess what? Doing a TLB flush that way is really horribly slow and impacts your performance negatively in your Linux kernel. So this is kind of a discouraging thing to see happen because we spent 5 years talking to the people in that community about why this was going to suck. And we kind of, this is why we lost Jonathan Neuschafer, right? He finally just decided he was sort of done with, runtime firmware and M mode. So Coreboot is going to take a very different approach. Come talk to us about it, how we're going to do it. But as of now, we're going to run kernel in M mode. That's going to be interesting, I think. But here's the thing we really learned. Open source wins. Right, so back in the day in like 1999, I had this thing, oh yeah, but open source always wins. And I really began to doubt that by 2009. I was really concerned that in spite of everything everybody had done, these sort of IP walls that had been set up were gonna kill us, right? And yes, there are blobs. I've got I'm not gonna claim there aren't blobs, but if you really look at sort of the number of blobs, they're declining over time. We do have new systems like RISC-V where we can avoid blobs entirely. Sooner or later, I don't care how big your company is or how smart your company is, you're not as smart as the rest of the planet. So this is kind of the core argument about why open source wins. And with that, I'll stop because and I wanted to thank the following wonderful companies for supporting us. But I did want to leave room for some questions. And so that's my 20-year history, leaving lots of details out. So yeah. Cool.
So you mentioned that open source always wins, but you're giving this presentation on a MacBook using OSFC.
Yeah, I know.
So what would it take for you to transition to a developer machine using Linux and using Coreboot?
An environment doesn't suck. I'd never been happy with the power management on the Linux laptops, and I really don't like the fact that I'm using a Mac. But and for years I just only used Chromebooks because I thought they were great until I could no longer plug more memory and disk into them. But yeah, I would like to get onto something that is running. I'd actually like to get on something around Coreboot, to be honest. But yeah, Coreboot would be okay too. Yeah. Not going to happen for a long time, but yeah. Well, actually, so if you watch the number of people creating new RISC-V silicon, it's actually exploding. So I shouldn't say that. It could happen very, very quickly in the next year or two. I've been amazed. Any other questions? Wow. All right. Well, the one thing David reminded me of, we kind of staged an intern death, and it was a pretty good picture. So go find him. And the other thing I forgot to mention, he was supposed to yell it out. One of the fun parts of the geode port for OLPC, we found a register called Bizarro. And it's kind of hard to describe how painful that chipset was, but maybe that is a hint. It was really amazing how hard two little chips can be to configure and bring up. But Audio came in one day and said, I've been dreaming MSRs in hex. And he said, this is my last port. So if that's it, then I'm done. No other questions. Okay. Thanks.